I'm Trace Dominguez. On this episode of Research Detectives, we're racing an invisible threat, a scary problem with the potential to affect all of us.
Scientists, physicians, and researchers around the world are battling bacteria so dangerous they're described as superbugs. They're so powerful they're immune to nearly every kind of antibiotic we know of. Bacteria are everywhere, on every surface of everything, from mountaintops to the bottom of the sea, and they literally live all over and inside of us, too. There are more bacteria inside the human body than there are human cells. But don't let that freak you out. There are tons of good bacteria out there doing everything from helping us digest our food to stimulating our immune systems. But bad bacteria, they can cause infections, and some of the worst infections are caused by bacteria that are drug resistant. When that happens, as the name suggests, the arsenal of weapons to fight these infections shrinks. People with pneumonia, tuberculosis, MRSA, E. coli, salmonella, and some sexually transmitted infections are in real trouble. Most at risk are patients with suppressed immune systems, those who need surgery, children, and people with long-term conditions like cystic fibrosis.
I'm Linda Bowman, and I am an adult living with cystic fibrosis. And I am an advocate for CF patients as well as the foundation. I do a lot of volunteering for the national office. I've done advocacy work. I'm really passionate about the current state of affairs and where we can bring to light the patient's views and voice and what it's like for the daily life of a CF patient.
Superbugs are especially dangerous for people like Linda Bowman. CF patients need antibiotics all the time because they have a thick mucus that fills their lungs and airways, harboring infections. Without antibiotics, it could be very dangerous for her, but with them, she can live a totally normal and inspiring life, filled with gardening, raising butterflies, and singing in a virtual choir. For people who don't know, what is cystic fibrosis, or CF?
So cystic fibrosis, what we know about it and what most people know about it is a lung disease.
What do you think that we can do to help people understand this problem of superbugs and antibacterial resistance?
You know, bacteria's role in my life and all CF patients is it's a destroyer of life. I mean, it sounds harsh, but it's so true. Bacteria is like the devil, you know, it's such a detriment, it's so dangerous. And I don't think many people understand that tremendous amount of anxiety that it causes for someone like me, for somebody who has CF.
So what do doctors say to you about antibiotic resistance?
Well, I'll tell you, it's it's a blow to hear that. When you're there for a visit, you're feeling sick. You know something's going on with your lungs. Your lung functions are down. You have a fever. You're weak. You're not feeling good. And then, you know what? I looked at your sensitivities. Your blood work came back. You're resistant to meropenem, you're resistant to tobramycin, and they go through the list. But it's a wow. It's hard to hear a doctor say, I don't know what I'm gonna put you on. Because if you came into my home, let's say, and you had a cold, if I catch that cold, it manifests into something much more than a cold because I'm always on. Like, my mind doesn't shut down. I'm very aware. If I go to the grocery store, who's coughing, who's sneezing. let me run the other way. Go to a family event. I've got to check in. Is anybody sick? And you can imagine that this has threads and tentacles that, they extend out, and it's every facet of life. So you're constantly worried about picking something up. And a lot of people think, it's just a cold, or it's some benign situation, but it never is that for the CF patient. So it plays a huge role, and I hate to say, in the demise of the lungs, but it's true. And if antibiotics stop working, you're left with possible lung transplant and or death. So this is what cuts the life short of a CF patient. And it's tough. It's tough.
Today, the penicillins are only one group of antibiotics among many. And in laboratories throughout the world, the search goes on for more.
It's been almost 100 years since the discovery of the groundbreaking antibiotic penicillin. That was in 1928. That finding set off a wave of research to find more antibiotics. In fact, antibiotics have been credited with helping the Allies win World War II. Penicillin was considered a miracle. It dramatically reduced the number of soldiers who died from infections. The antibiotic was so effective that infections that previously killed were now cured.
But bacteria, they didn't give up. They fought back, finding new ways to defeat our antibiotic drugs. They are evolving and changing so quickly that they are outpacing new drug development. Research detectives all over the world at hospitals like this one at the Jackson Health System in Miami, Florida, are on the front lines trying to find new weapons in the battle against the superbugs. Institutional-wise, individually, globally, how are we handling this? What are we doing about it?
Antibiotic resistance is not isolated to a room in a hospital or a clinic or a city or a country. It's a global problem. If we don't do anything about this problem by the year 2050, we're going to be spending $100 trillion of the global GDP, the gross domestic product, just in combating antibiotic resistance. We're going to have more people dying from antibiotic-resistant infections than dying from car accidents, or dying from cancer, or dying from diarrhea in developing countries. So this is a problem that needs attention, and a lot of work is being done globally, but there's more work that we all need to do. We work very hard in preventing and creating patient safety. The other thing that we do is that when people come in with an infection, we want to make sure that we don't spread that infection to other people. So we want to prevent outbreaks. We don't want outbreaks. We don't want epidemics. So that's part of what we do.
An important part of the fight is using antibiotics wisely.
You mentioned this a couple of times with antibiotics, that the length of time matters. 3 days, 7 days. Why is that?
So we only use antibiotics when we need them, and we use the right antibiotic so we don't create what we call resistance. That means that bugs already say, that medication that you're giving me, not good for me. I already developed a shell or a way of fighting you. So we want to make sure that we prevent that, because otherwise these germs become very strong and become superbugs, and then it becomes harder to kill, and then they can also get transmitted to other patients.
How is it that a little bacteria can become resistant?
Well, so the way I tell people or my students is bacteria are very smart. Bacteria multiply in the millions. A bacteria doesn't need 9 months to get pregnant like a human being to have another child. Bacteria are very promiscuous. They have different mechanisms to share their genetic code and to share their mechanisms of resistance. They don't need to have sex to transmit things to each other. In humans, you sort of need to replicate and have another human being in order to pass something genetically, right, to your other generations. Well, bacteria don't. So in between species, they can pass mechanisms of resistance. So that's when we say they're promiscuous. They don't need to be from the same family to transmit resistance, and they multiply in the millions.
What do you do in the hospital to protect patients from bacteria?
One of the important things to know is that regardless where you practice, in a fancy private institution, in a developed country, wherever you are, there are standards of hygiene that need to be maintained to prevent patients to getting any bug or any superbug. So what are those standards? Well, we need to make sure that when you're coming to the hospital, the room is clean. So one example is right here, is the setup, right? We have a team of people, and it's a village. It's a village that actually takes care of making sure that when patients are coming in, the environment of care is clean and protected. So we have environmental services. They're more than just a maid service. The environmental service workers are key to the function of the hospital. They make sure that the room has been terminally clean after the last patient was here. So we have curtains that are disposable curtains. We change the curtains. We need to make sure that the bed is clean. There is a mattress. Those mattresses and the entire bed goes a deep cleaning. That doesn't happen when you go to a hotel. We don't want to bring and share bugs between rooms or within patients. When we bring new equipment, let's say the patient is getting an ultrasound at bedside, we need to make sure that that equipment is being cleaned before and after encountering that patient. And if that patient is being transported, we need to make sure that when they bring the stretcher to take that patient to wherever they're getting a procedure, that stretcher or wheelchair are also clean before and after we transport anybody else. So these are just some of the basics. Then in addition to the cleaning, we use this robot, that's our machine that has UV light, and that's an extra layer of protection. And usually, they put, it has several towers, so one of the towers goes in the room, the other tower goes in the bathroom, and we do cleaning. The robot will measure all the surface in the room, and it will determine the duration of how long they need to do the cycle. So that's an extra layer.
Researchers are working to disrupt superbugs by developing new antibiotics, and they're turning to nature. They're cataloging a massive database that could help yield strong new compounds that can eventually defeat drug-resistant bacteria and stop the superbugs. Here's an interesting fact I think you should know. 1/3 of all the FDA-approved drugs in use today originated in nature.
I'm at the Natural Products Discovery Center in the Herbert Wertheim UF Scripps Institute in Jupiter, Florida. This is home to what is believed to be the largest collection of microbial strains on the planet.
It took scientists and pharmaceutical companies 100 years to assemble the collection. There are more than 220,000 samples. Every one of these vials contain freeze-dried, purified microbes that were collected from dirt, seawater, and extreme environments all over the world. The microbes evolved specifically to defend microbes against other microbes, and for that reason they hold enormous potential to become the next antibiotic. Within the genetic material of every single one of them lies the recipe for complex natural chemicals that could become new, more powerful antibiotics. Just getting the samples to Jupiter, Florida was a massive undertaking. It took 2 years to move and assemble them. Professor Ben Shen and his team are cataloging the collection and building a database. It's a way to get a better understanding of the building blocks, exactly what each microbial strain is made of.
So downstairs are those vials, but this is where the work actually begins. Here, they crack the vials open, culture what they find inside, and then sequence their DNA to see if there are any compounds they can use for drugs. Can you walk us through the process of cracking those vials open and cultivating what you find inside?
I would argue there's probably 3 kind of conceptual steps. The first step is that walk into that room, among the 120,000, you pick up the one that you want to study. Okay, so we will accomplish this by making all the genome available to the genome mining. So somehow by looking at the genome and using all the knowledge we or the community has studied over the years, we were able to pick this or 1 or 10 or small number of the strands we think most likely will be productive.
So here you blend biochemistry, organic chemistry, and microbiology?
So we grew them in the lab, and where you see all these shakers, petri dishes, and we essentially force the organism to produce that particular compound. And so this is in the biochemistry and entomology stage. And then the last stage is organic chemistry. Once we produce this compound, and we know the compound produced, and then we need to produce in large quantity and isolate them in the tube, and then we can evaluate the compound. Will this compound truly say will give the phenomenon, give the the bacterial killing properties. And that is pretty much the end of our study in the fundamental level. And then we make this available, patent it, and then translate it into, say, biotech industry or pharmaceutical industries. They will take our lead and develop it eventually into a commercial product.
One of the scientists in Dr. Shen's lab describes the process this way.
I think a good analogy would be to consider the bacterial cell itself as sort of an assembly line. So it knows how to put together specific chemical modifications to create the final product that we're interested in. But, of course, it needs instructions on how to do that, and that's written in the DNA. So if you want, you can think of the DNA as sort of a really big recipe book.
Oh, wow. That is a good analogy.
I think so, too.
Why don't we just synthesize these just on our own? You know, we take a computer and boop, 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 we make our own stuff.
Yeah, exactly. So these chemicals are actually so complex that humans actually aren't capable of producing them yet. It's actually the bacteria's millions of years of evolution that's been perfectly able to harness these bacteria to produce these really specialized compounds.
Nice. So we're just kind of harvesting them from them after they've already made them.
Yeah, it's been millions of years of evolution have gone into this perfect genetic code that's inside each bacteria to produce these compounds.
Cool.
Dr. Luis Carvalho and his team at the Wertheim UF Scripps Institute are working to get a better understanding of exactly how bacteria are morphing to become drug resistant. They're working to find new ways to treat lung and other infections caused by germs called mycobacteria.
We're very interested in tuberculosis, human tuberculosis, caused by the bacterium Mycobacterium tuberculosis. So it is a very ancient disease, right? I'm sure you heard about mummies that have been unearthed and discovered to have bone tuberculosis, right? So it has been with us for about 100,000 years. It's a bacterium that in nature, it doesn't infect any other animal, only infects humans. So it's human-to-human transmission, and there is a potential to eradication, right? In adults, it's mainly a pulmonary disease. In children and immunosuppressed individuals, it can happen anywhere in the body.
So why is it that germs or bugs become resistant to antibiotics?
We do mainly two things in my lab. We try to understand how bacteria become resistant, right, to try to interfere with that if possible. And we're looking for new compounds that might be very hard to elicit resistance. So it is a frequency, it is a numbers game. It will appear. If an antibiotic is used in humans, resistance will appear. But if it appears in 200 years, it's much better than it appears in 2 years.
I guess in 200 years, right, we'd have a different tool. So y'all are looking to better understand how bacteria work so you can fight them?
We study bugs and we work with bacteria. We also work with proteins that are derived from this bacteria, and we try to understand from a very fundamental chemical and biochemical standpoint how these enzymes do their business, do they work, how they work together forming metabolic pathways, and how these pathways impact in virulence, in the ability of the bacteria to kill or to cause disease, but as well on antibiotic sensitivity and ultimately antibiotic resistance.
What do you wish that people knew about superbugs?
So don't self-diagnose. Take antibiotic only with prescription and for the entire duration and format of the prescription. And if you have a lot of money, send it to people that are doing antibiotic research, because pharmaceutical companies are no longer doing it.
Why aren't pharmaceutical companies doing this?
So the reason that a number of pharmaceutical companies have stopped really pursuing antibiotic research is because it's not super profitable. They are for profit, so they're not charities, and therefore they have to go after something that, is going to return their investment. Unfortunately, there is no one picking up the slack, right, so to speak. So we will need in small biotechs, universities and institutes to develop that for us. It costs about $1 billion to make a new antibiotic that you might take for 3 days for an ear infection. It's different from, for example, a cancer therapeutics that you're going to take for 6 months and you can charge as much as you want. So it's an economic problem, not a medical problem. It's just not profitable. You invest $1 billion and you get 100 million. It doesn't work.
So what are you doing to help prevent this from happening?
So support comes in many different formats. The government, right? So NIH, NSF fund this type of work. There is private institutions that also put money in research, even though, including pharmaceutical companies, even though they're not developing drugs, antibiotics for human use, they are still keen on supporting certain activities, which is great for us. And some significant amount of money comes from donation from the Gates Foundation, for example. Wellcome Trust, another good example. So it's a tough ground. It's a tough ground for research.
And yet, here we are.
And yet is absolutely needed, right? Otherwise, in a few years, antibiotic resistance will kill more than global warming.
It's a tough fight. It's a global problem. Fortunately for most of us, an important weapon is right within reach: soap and water.
Hand washing is so important, the CDC made a video about it.
First, wet your hands with clean running water. Turn off the tap and apply soap. Then, lather your hands by rubbing them together with the soap. Be sure to lather the backs of your hands, between your fingers, and under your nails. Scrub your hands for at least 20 seconds. If you don't have a clock nearby, keep scrubbing until you've sung the happy birthday song twice. Rinse your hands well under clean running water. Dry your hands using a clean towel, electric hand dryer, or air dry them. Washing your hands using the steps we just demonstrated is very important to get hands completely clean.
Now that you've seen the right way to wash your hands, remember this information too. Keep cuts clean and covered. Always clean your hands after touching or feeding animals. Make sure food is prepared and stored at safe temperatures. Practice safe sex to prevent sexually transmitted infections. Don't misuse antibiotics. Follow your doctor's or pharmacist's instructions to the letter.
How closely are you following the science of this?
I think I'm following it pretty closely. I, of course, am always reading on NIH. I've been part of several focus committees with the foundation on clinical trials. I'm in PubMed all the time looking things up. I constantly am asking doctors, plus I do my own research. I'd rather know. I refuse to sit in the dark. It's just something that I'm not made of.
Linda Bowman says we all have a part to play in fighting superbugs.
There's no easy answer, but there are practical things that we can be doing to fight back against superbugs. Being proactive in, if you think you have the flu and you're going to work and you're coughing and you're spreading, droplets, that's a problem. And if people understood in a bigger way what a big problem this is and that people's lives are at stake, just being a little mindful, I think that would just make a big difference.
It may not sound like much, but every step is important in the race to defeat the superbugs. I'm Trace Dominguez. We'll see you next time on Research Detectives. Keep your hands clean.